So it's been a couple of weeks since we had a lecture. Ended up being a long Diwali break. And as I mentioned last time, we need to shift through a 3-lecture per week schedule for the coming month. And I will start that from next week so that we can catch up and be on track to finish on time. Some of you have emailed me your homework, so if you have done it electronically, you can email it, the PDF file, to me as well. Those of you who have done it on paper, and if it's ready, you can hand it over to Gaurav. He usually sits in CG23, so ground floor C block. So you can give it to him, but definitely turn it in latest by Monday. After that, I'll have to put some penalties for late submission. So let's get started. I'm going to share my screen. Okay, so we will start looking at microwave network analysis a lot more formally. We have sort of already seen elements of this throughout the class so far, but we'll formally look at this. So this is chapter 4 of POSAR, and there are sections here which I would like you to just read on your own. They just sort of cement the ideas a lot more concretely in terms of the equations and stuff. Today, I'll just go through them very briefly and point out the things which you can just read on your own and talk about the more practical matters when it comes to actually using these ideas to analyze circuits. So again, there is very nice introduction to this chapter, but many of these things we've already discussed several times, and it's basically repeating the same idea that low frequency circuits dimensions are small compared to wavelengths, so you can define voltages and currents at any point in the circuit, and there is no negligible phase delay between different parts of the circuit. And this allows you to simplify things and basically use Kirchhoff's voltage and current laws and the impedance concept, which is just the ratio of voltage to current across an element, and use that to analyze these things. In general, this is not applicable at high frequencies, but the purpose of microwave network analysis is essentially to create a similar method like the standard circuit theory, where you can use similar ideas. And here, the essential point is that you can separate a microwave structure into sort of 2 parts. One which is the actual structure where all the physics is going on. And then there are the terminals of that particular microwave circuit or device or structure, where you are actually going to be interested in knowing the properties. And this is almost universally true for most practical cases. And microwave network analysis essentially allows you to bridge this, that how you can, once you have calculated the properties of the full structure, you can define it completely by just properties which you measure at the terminals of the circuit. And in any ways, it's these terminals which allow you allow this object to interact with other objects in the most general case. So that's what makes it useful to and very powerful to use this method. Of course, there are situations where you need to really see what's going on with the fields, the electric and the magnetic fields inside the body. And this would be needed in order to understand any non-ideal behavior you're observing in the properties we measure at the terminal. So the properties are still, the system is still uniquely defined by what's happening at the terminals. But if it doesn't make sense and you want to fix it, you have to look at what the fields are doing in order to interpret what's going on and then change it accordingly. So this distinction of when you need to look at the full field distribution over the entire structure, like one can do with finite element simulations. But the kind of simulations we have seen in the last few lectures, for example, when we have been analyzing transmission lines, we have also been only interested in the properties at the terminals, because that's where we put the ports and we compute the properties of like reflection and transmission. But if something goes wrong, so for example, we talked about the CPW transmission line, which has, let's see, I'm going to draw here, which has 2 ground planes, a center conductor, and so this is all metal, right? And you connected the ports here, and in microwave office we did it like this, -1 on for the grounds, and right now we are trying to design a transmission line, so we kind of expect what the properties of transmission and reflection should be, so which is basically unity transmission and as small a reflection as possible. But if you see something strange, like for example, there is some big dip in your transmission spectrum, then you cannot figure out why this is happening by just looking at this properties, right? This transmission curve. And one possibility is that this CPW line is not working properly because we did not bridge the 2 grounds with proper vias or air bridges, and that is causing a slot line mode to emerge and giving rise to some weird behavior like this. Right? Otherwise, just by looking at the structure and by looking at the things, you can't see why there should be a resonance. And maybe this is coming because there's a slot line mode. And as I explained last time, the slot line mode has these 2 ends at the same potential. So it looks like a transmission line with 2 shorter ends on either side. So that could have a resonance, and that mode could mix with your CPW mode and give rise to some behavior like this. So what I'm trying to say is that if you see something strange, then you might have to go and see what's going on. What is the field distribution in this entire region, across the whole structure. And if you look at that, then okay, at this frequency, the slot line mode is getting excited. And these kind of simulations are possible. This kind of visualizations are also possible, not in microwave office to the best of my knowledge, because it doesn't really give you access to the fields at different points. But in other softwares, some of you might be familiar, like COMSOL and also HFSS from a company called ANSYS. So there you can actually see how the electric field and the magnetic field are varying across these conductors. And you go to this particular frequency and you see how the system is behaving, and then you can see that, okay, the fields are not where they are supposed to be. So that's how you know that something is wrong, and then you fix it, and then your scattering matrix, the properties measured at the terminals, will be correct. Okay, so this is something you have to use your judgment to decide when to use one method versus the other. Of course, if you're using finite element simulations to calculate the scattering matrix in any way, so then you do have access to the full structure, not in a software like Microwave Office, where it only keeps the solutions at the end of the terminals. Though I've actually never tried to look into it in great detail to see whether it allows any field distribution information to be obtained. Okay, so that's essentially the idea, and I would recommend that you read through this introductory part of the chapter as well, including these sections where they define formally, how you think about voltages and current. Because in general, at microwave frequencies, the measurement of voltage and current is difficult or impossible, because essentially you need to have access to terminals. So it can only be done at the end, and even then you don't have ideal voltmeters and ammeters at these frequencies because everything has a source impedance. So you have to resort to a different method to actually when it comes to measurement. But for analysis purposes, you can define voltages and currents as long as they are on the terminals, or you have a well-defined microwave structure like a transmission line where you also know how the voltages and currents change through the structure and not just at the terminals. So, defining your voltage as the line integral of electric field and the current as the line integral of the magnetic field gives rise to a unique definition of voltages and currents only if you have this TEM type of modes. Otherwise, the path you take for the integration will start to matter. And that's what they sort of explain here and formalize it. But, as I said, you can read through this. This is not very relevant in order to really use these ideas. But this then gives rise to these three sort of guidelines. So you want to keep in mind that voltage and current are defined only for a particular waveguide mode. And they're defined so that the voltage is proportional to the transverse electric field and the current is proportional to the transverse magnetic field. So this is basically what the definition earlier was. What they're trying to say here is that it only makes sense if your structure in general supports different modes. Like, for example, the bad CPW line we were talking about can support a CPW mode, which is a TEM mode, and it can also support the slot line mode, which is a different type of mode. And there is no concept of defining a general voltage. You have to say that, okay, in this mode, I can define a voltage because it has a precise form and I can define it, and then it becomes unique. So that's the most general thing. And in order for it to be useful, like this definition, there are some arbitrary scalings you can have. It's better that these equivalent voltages and current are defined in such a way that voltage times current, like how we normally define power, also gives you the power flow of the waveguide mode. Okay. Now, this might seem strange, but there are actually several equal ways of defining this. It's just, scaling how the voltages and the currents are being defined. And it's actually connected to the third point, which is the ratio of voltage to current for a single traveling wave should be equal to the characteristic impedance, right? So remember, we had this Z0 defined as V0 plus or I0 plus. So for a single traveling wave, that's what they mean by that we either talking about the right propagating wave or the red propagating wave. It's not just the general ratio of V to I, right? Because the two waves have two different voltages and currents one need to keep in mind. And here they say that this impedance may be chosen arbitrarily, but it's usually selected to be the wave impedance of the line. Okay, so this is the most standard thing, and this is what we have been looking at, the square root of L over C for the telegrapher's equation analysis we did for a transmission line, which is composed of sections of L's and C's, with L and C being the inductance and capacitance per unit length. That is also the wave impedance of the line, and that's the most natural definition. But you can choose some arbitrary definition if one likes. It's not very useful, but it's possible to do that. Okay, so when you do this for a TEM transmission line, we've already seen this this kind of equation that the voltage at any point Z along the transmission line can be written as a sum of right propagating and left propagating waves. And similarly, one can write it for the current. The current equation has a minus sign here because of the way these things are defined. And this here is actually the first simple example of how we can talk about an extended object like a transmission line in terms of its properties at the terminals, and an equation like this, which tells you what's happening inside this object, right? So you can still, as we will see later on, you can use this equation to actually determine the properties at the end of the terminals. And a particular example, I'm not going to work through it, but this is something useful to try. Particularly if you are interested in sort of writing down the time domain response of a circuit like this. So this is just, of course, a simple LC circuit. So if I draw the same circuit here without, so I have R, L, C, and B. So I have removed the transmission line. So all of you, should know how to, for example, write down the differential equation of this circuit, right? So you can choose a variable. Let's say we choose the flux across the inductor. Then we know that the current through the inductor is phi over L. This just comes from the fact that phi is Li, right? So, and then the current through the capacitor is equal to Q dot, right? So I through the capacitor is equal to the derivative of the charge on the capacitor, but Q dot can also be written from the fact that the voltage across the capacitor, V, is Q is equal to C into V, but V is nothing but phi dot, right? Because the phi and the C, the voltages are across the same terminals here. So that then makes this here C phi double dot. So then you can basically write down the Kirchhoff law that the current on the inductor and the current on the capacitor should be equal to the total current here. And then you bring in the voltage source and match the voltages, and you can write down a differential equation. And you know what that differential equation is going to be look like. It will be something like this: phi double dot plus 1 over R phi dot C plus 1 over LC phi, sorry, not phi. Phi is equal to V, I think will be over RC. Right. So this is just the second order differential equation for a harmonic oscillator, where V is now some sinusoidal signal, right? So you know how to solve this. But if I now say that, how would you do that for this circuit where the transmission line has been introduced? And you sort of intuitively know that if the characteristic impedance of this transmission line is the same as this source resistance, then this transmission line's job is only to move the signals from this end to this end and this end to this end. So the dynamics as experienced or as explained by this differential equation shouldn't really change, right? Because it's not a different system. The only difference now is that there is now a time delay between what's happening at this end versus what's happening at this end. And then you can use this equation to equate this voltage here, which is the source voltage, and some properties of the circuit element as given by, sorry, not the circuit, the dynamical properties of the LC oscillator here, which is completely given by the dynamics of phi. You can equate the two and then get expressions for what V plus and V minus would be. Okay. So this is a good exercise to try. I think it's actually there in the next homework, which I will be sending over the weekend. And the point here is that if you are, this LC circuit could have been something more complicated, and maybe you know how to write down the equation of motion to understand its dynamics. But now you're interested in looking at what the reflected wave is. How do you calculate that? For the simple LC case, of course, we can use the impedance approach, because we know that the reflection coefficient gamma is just Z minus Z naught over Z plus Z naught. So if you want to calculate the reflection coefficient, which is a steady state property using this, you don't have to solve the differential equation. It can be done a lot more simply. But if you are actually interested in the time dynamics, that how does the reflected wave change as a function of time, then how do you relate that reflected wave to the dynamics of the system? So it will be related to the source voltage, what's happening in the LC circuit, and how this equation here connects by setting the boundary conditions. So all you have to do really is that in this circuit, this point here, the voltage is the same as the voltage across this other point, which I'm sort of artificially drawing right next to it. The only difference is that now this point has moved to this end of the transmission line, and this point has moved to this end of the transmission line. And you need to use this equation to equate the voltage here and the voltage here. Okay, so this is sort of a simple example which connects these ideas of the properties at the terminals to what is happening in that microwave device, in this case, of course, it's a simple transmission line. Okay, so let's move on. Just give me 1 second. By the way, are there any questions here? This can be a little subtle to follow, but it's just matching boundary conditions and using this wave equation to equate things. So check if anybody else is waiting. Okay. So yeah, this of course we have already seen. Yeah. So there is this idea of having different kinds of impedances here. So this is again not really relevant from the practical usage part, but this sort of completes the picture here, that there are different impedances, some of which we have already mentioned, and you need to be just aware. And so this section here summarizes is that for a general medium, defined by mu and epsilon, that is this intrinsic impedance of the medium, right? So I have been mentioning this in the context of the impedance of vacuum, which is square root of mu naught over epsilon naught. And this impedance is only dependent on the material parameters of the medium, right? So for free space, the material parameters are mu 0 and epsilon 0, and is equal to the wave impedance for plane waves, right? So the fact that we are now specifying the wave impedance for a particular type of wave is specific. And in this case, the intrinsic impedance is the same as the wave impedance for the plane waves. The wave impedance itself is defined as the ratio of the transverse electric field to transverse magnetic field, the amplitudes. And this is now characteristic of that particular type of wave. So for a general case, you cannot just say that for this system, this is the wave impedance, because it will depend on whether it's a TEM wave or TM wave or TE wave. And each of them you have to define separately. And then finally, you have the characteristic impedance, which is what we have been looking at. And this one is uniquely defined for TEM. And it's also, it's not possible to have that for TE and TM modes, because you cannot uniquely define the voltages and currents. And the previous section here sort of discusses that in some detail, and you can read through that if you're interested in understanding why the different field distributions give rise to prevents you from defining voltages and currents in a unique fashion. Okay, so yeah, so this is just sort of summarizes that. So read these two sections, and you can contact me if you have any doubts about that. So we now move on to one last property here, and here also I wanted to emphasize a slightly related fact, which might not be so obvious to all of you, because you've just never thought about it in that way. So this section is actually talking about how these impedance functions are like what kind of properties do they have in terms of their symmetries. And there are certain things which comes about because of certain physical constraints of what happens in a real situation. So the this equation here, V of omega equal to Z of omega into I of omega. This is what I was referring to as the subtle equation. Okay. Now, this is nothing new. We have, of course, seen this V is Z into I all the time, but it's not so obvious what this means. Okay. This actually makes it very precise. What we are really saying is that the voltage at a particular frequency is equal to the current at that particular frequency multiplied by the impedance at that particular frequency. The bottom equation says the same thing, but it's not true in general. When you're working at very low frequencies or where the properties of Z are not frequency dependent, then it's okay. Then you can write it like this. Okay. It is also doesn't mean, so this also means that V of t is not equal to Z of t into I of t. Okay, what does Z of t even mean? The point here is that these are now looking like real space and Fourier space, right? So if your impedance is frequency dependent, then the correct definition is really this. And anything else you want to do, you have to use this equation. Then if you want to look at the time domain voltage, then this essentially will become, you have to take an inverse Fourier transform, and that will actually give rise to a convolution in the real space. So as long as you're implicitly assuming that you're always going to be talking about only one frequency or DC, then the simple version of this equation is okay. But otherwise, this is what one really means. And this section essentially talks about the fact that because your voltage as defined here should be real, it gives rise to certain constraints that any general impedance has to have this property that R of omega should be even in omega, and X of omega has to be odd in omega. I'm forgetting the name of this thing which we learn in solid state physics, which connects to we need to look at epsilon as a function of omega, and we get a similar constraint that for physicality, for physical system, real systems, you need to have this kind of behavior. So this is sort of a, I think it's called Kramer's chronic relations or something.
Yes, a Kramer relation. Kramer chronic.
Yeah, exactly. So this is sort of a version of that. So what it means that if you're constructing any impedance, they will have to obey this kind of properties. Okay, and then you can extend that to the reflection coefficient gamma, which also is strictly speaking defined for every frequency separately, and then that also has this similar consequences because of the fact that R and Z are of a particular type. So here the R of omega and X of omega is referring to the load impedance in this reflection experiment, and Z naught is the characteristic impedance of the port with respect to which you are measuring these properties. Okay, so basically I've sort of gone through this very quickly and highlighted the important parts, but read that section up till the end of 4.1 carefully, and it's fairly self-explanatory and nicely written. Okay, so now we move on to talking about the concept of these networks. And once you are able to define these voltages and currents as terminals, if you the most general case is that you have an n-port network, which means this network has n sets of terminals, which means n pairs of currents and voltages to talk about. So you can basically write this in this kind of a matrix form, the most general form. So going from V is Z into I for just a one-port network, right? If you just have a resistor or a complex impedance. In general, you can write for the n-port network an equation, a matrix equation like this, where this lists all the voltages at the terminals from 1 to n. This lists all the currents from 1 to n. And then you have an n by n matrix, which tells you how the voltage at one terminal is related to the currents at all other terminals, right? All of these coefficients need not be finite here. So V1 is going to be Z11 times I1. So that's the dependence on current I1, Z12 times I2, and Z so on and so forth till Z1n times In. Okay. So if you look at this kind of a picture where they have drawn this generalized n-port network, the waves, they've actually here drawn them in terms of current and voltage waves at those points, whereas the above equation is actually the voltages and currents at that terminal. These are not the voltage waves, okay? Because this figure is referring to a later concept as well. But what it means is that if you have a general network, I mean, this is obvious, the voltage you measure between these two terminals is going to depend not only on the current between those two terminals, but also on the current at all other terminals as well. Right? Because all of them can together give rise to a voltage drop at this particular point. So this is the most general way of writing, and this here will be called an impedance matrix. Okay, so this is one way of defining the properties of an n-port network is in terms of its impedance matrix, which in general will have n square elements. And not just that, each element could be complex. So there's like 2n squared elements, but just in a little bit, we'll see that there are certain symmetries which come about for many practical situations. So this is one way which is useful for calculations, because when you have given a microwave circuit, and particularly for like a microwave circuit which could contain many different elements, because there you know how to apply Kirchhoff laws and calculate currents and voltages, and you can calculate these impedances. But when it comes to measurement at the terminals, it's a lot more convenient to measure these ingoing and outgoing voltages. That's actually what is done practically. And when you use those variables instead of the voltage and the current, then that gives rise to another type of matrix, which is what we'll come to later. Okay, so the impedance matrix is just the generalization of the simple equation that V is Zi to an n-port network. And similarly, you can sort of invert this equation, and instead of this, you can define a matrix Y, which now relates the current to the voltage, just like you have I is equal to Y into voltage, right? So it's the inverse of the resistance or the impedance for a one-port case. And in this case, it's the matrix inverse of the impedance matrix. So these two are completely equivalent ways of defining the properties of a n-port network. Okay. And as I said, these are easy when one has actually a circuit representation of the network, and then you can calculate this fairly straightforwardly. But what exactly is the definition of each of these elements? So for example, if I look at the impedance matrix, so Z of ij, so this is one of these elements here, okay? It's the voltage, excuse me. Sorry, just give me 1 second. Yeah. So it's the voltage on terminal I divided by the current at terminal J, with all the currents set to 0 except for the terminal J itself. Okay, so this is what the meaning of one of these elements it means here. So it's independently telling you what would happen if there was a current at a particular network, how much voltage would it drop at another point in that network. So of course, J need not be I, because J and I can be different. That's how you go across the network. But it's important that no other terminal is passing any current. Okay, so here it says that in words that the Zij can be found by driving port J with current Ij and open circuiting all other ports so that there is no current flowing through these ports. So what does the open circuit? So you have this, let's say, take an example of three port network. They mean that if this is the one you are, if this is say J and this is I, then you want to pass a current here and leave this open and measure the voltage drop across this. Okay. If you wanted to do it for the other one, Zik, then you put a current source here and leave that one open circuited. So that's what it means. So when you know this, the reason this way of thinking about it is useful is it's sort of telling you that each of this element gives you the effect of passing a current at any point at one of the terminals in the network on the terminal you are interested in looking at right now. And then if you add all their effects, because of course this is a linear system, everything will just add up. So if you have many currents, then you have to add up all the other terms here. But if you wanted to measure this quantity or calculate this quantity Zij for a particular microwave network, then this is what you need to do. And same goes for the Yij as well. Okay. So as I was saying earlier, that in general, for an n-port network, the matrix is n by n in size. So there are 2n square independent quantities. But in practice, the symmetries which I had mentioned, that they're either reciprocal or lossless or both, right? So we did talk about lossless systems earlier, but when you do that, it minimizes the number of independent variables which define this n-port system. So for example, symmetric here basically means that it's a system which doesn't have any active devices, which means no voltage sources or anything inside the network. Obviously, at the ports, we always have these sources. It also does not contain any so-called non-reciprocal media. No, it's kind of funny to say that a reciprocal system is something which does not have non-reciprocal systems, but what are they? We will look at take an example of non-reciprocal media much later towards the end of this course. But they give examples like ferrites and plasma. So some magnetic materials called ferrites can give rise to some strange properties, which is basically non-reciprocal behavior. And when you have that, you see that your elements are also symmetric. The impedance and admittance matrix are symmetric, so that Zij is equal to Zji and Yij is equal to Yji. So this basically means that if you are putting a current at one terminal and measuring the response at a different terminal, if you just interchange those, then there will be no difference. It will behave exactly the same, which means that Zij and Zji should be equal. And if the network is lossless, and this of course is sort of obvious, you should have that if your network is composed of different circuit elements, then they should all be purely imaginary, because imaginary basically means inductors or capacitors, and real means that there's some resistance. So of course, the moment you have resistance as part of your network, then it's going to dissipate energy. So it's not going to be lossless. So what it means is that if you have power coming in and there is power coming out from all the ports, so they will not be equal. Like the outgoing power will not be equal to the incoming power, because some power will be lost inside the network as well. So a lossless network is something which doesn't lose any power inside the network, which basically translates that you have to construct it out of imaginary impedances and admittances, which essentially means inductors and capacitors, which have no resistance, ideal inductors and capacitors. Okay, so this basically means that you don't have to worry about the real part. And then if it's reciprocal, which most linear circuits are, then number of elements you need to define, independent elements you need to define, an n-port network goes away. Okay, so the next two sections called reciprocal network and lossless network actually prove this. So you can go through this proof. It's fairly straightforward. So let's look at one simple example so that you get a sense for how these values, which are the elements of the impedance matrix or the admittance matrix, how do they connect when you to the actual circuit you have in front of you. So here's a very simple example of a T network. So it has three impedances, ZA, ZB, and ZC as shown, and it's a two-port network, so 1 and 2 on this side. And we want to figure out, so this means that it's going to have an impedance matrix, which is going to have 4 elements. So Z11, Z12, Z1, and Z22 into I1 and I2. So now you want to know what these 4 elements are. So because the circuit itself is made of impedances and your impedance matrix's elements are impedances, it's sort of natural to connect the two of them, but obviously they are not the same, or they need not be the same. So this gives you an intuition of what it is. So you have to use the definition of how we defined what Z11 is. So here is the definition. Z11 is V1 over I1, right? Because both the indices are the same. So you're passing current I1 on terminal 1 and measuring the voltage V1 while keeping I2 equal to 0. So keeping I2 equal to 0 means that you leave this connection open, and then passing a current I1 here and measuring the voltage drop V1 means what? It just means that if you pass a current here, because this is open circuit, that entire current is going to flow like this. And then you're just going to measure the sum of these two impedances, right? So here it's obvious. So this is what I was saying, is that if the circuit is in front of you, then the impedance matrix elements are easy to calculate. So already you see that the Z11, which is this term, is, it's not one of these impedances here. it's actually equal to the sum of two impedances, ZA and ZC. Right? So that's Z11 for you. Then if you look at Z12, then you need to, so it says, can you measuring the open circuit voltage at port 1 when current I2 is applied at port 2. Right? So you have to measure the voltage here when a current I2 is being flowed in this direction. So how does one do this? I mean, it's actually shown here that this is going to be equal to V2 over I2, which is the voltage here divided by the current going through that into this ratio ZC over ZP plus ZC. And then that simplifies to just ZC. Similarly, Z22, which is now on this side, so it's V2 over I2 with I1 equal to 0, and that's just going to be the sum of these two guys. So you get ZP plus ZC. And since it's reciprocal, and you can actually verify this also in this case, you will, it's a linear system. Z21 will turn out to be Z12, and both will be equal to ZC. So even though this the circuit was constructed of ZA, ZB, and ZC, the impedance matrix elements are ZA plus ZC, ZB plus ZC, and ZC. Okay. So this example sort of tells you how these things tend to be related. Now, this is not always possible to calculate for an arbitrarily complicated network, because then you have to sit and, I mean, it's not impossible to do it, but it becomes very hard if the circuit becomes very large. Of course, computer softwares can do this routinely, but in terms of writing down the equations and solving it, it'll become quite involved, unless there are some simple symmetries you can use to get intuition about what the values would be. Okay. So that's the how you compute impedance matrices. Similarly, admittance matrix is the same thing, but now you invert, take the ratios of current to voltages and not voltage to current. So you can verify for yourself by computing the impedance, the admittance matrix for this same circuit, and seeing that it's actually the matrix inverse of the impedance matrix. So now we finally come to the idea of the scattering matrix. And again, we have actually already seen this. This essentially is there because at microwave frequencies, you cannot measure currents and voltages. There are no ideal voltmeters and current voltages. It's a lot easier to measure these reflected wave, which is a ratio of the wave which is scattered with respect to what you have sent in. And that's because in order to measure that, you don't need to have ideal voltage, and so ideal voltmeters or current meters. So you just change the quantities which define your network, and which go back to this figure here. This figure here. If now at each port you define these four quantities, which is the voltage and the current incident, and the voltage and the current reflected or scattered, hence the word scattering matrix, then the relationship between these quantities at all the different ports is again exactly equivalent to the information given by the admittance or the impedance matrix. And one can interconvert these things with one slight but subtle point to note is that while the impedance matrix is purely a property of the network, the scattering matrix assumes some characteristic impedance with reference to which you are doing the measurement. So, but it, in practice, it doesn't make any difference. So how are these things now related to each other? Okay. So the current wave and the voltage wave, they are sort of equivalent. One can go from one to the other. So all you need to know is what is the relationship of all the reflected waves or the scattered waves. So those are represented by V1 to Vn minus, superscript minus, to all the incident waves. Okay, so this is a different way of thinking about what we said earlier, that I put some current in a particular terminal and I want to know what the voltage is in some other terminal. That is the impedance matrix element. Here, what I'm saying is I'm going to put in some signal V1 plus and on port 1, and I'm interested in knowing how much signal comes out of, say, port 2 or any of these ports. That coefficient which relates those two is the scattering matrix coefficient, right? So the first one is V1 minus is equal to S11 into V1 plus. This is just the simple reflection case. And if you only had a one-port network, then this is all you have, right? What is the reflected wave given the incident wave? That is essentially gamma for a single port network. So S11 is basically gamma for a one-port network. And then you do the same thing for other ports. Now, V1 minus is also equal to S12 into V2 plus, which means that if I send in a wave with amplitude V2 plus on port 2, then what is the wave which is coming out of port 1? That is given by the coefficient S12. What is getting reflected back at V2 is given by S22. Okay. But in general, if you have all of these or some of these, you have to sum all the different contributions, just like you did for the impedance matrix. Okay. So this now here in the matrix form is written here. The vector which define the 1D matrix which defines all the reflected waves on the endports is given by the scattering matrix multiplied by the vector composed of all the wave amplitudes incident on all the endports. And again, in order to calculate this, or the definition of what S1J in a more formal term, is that you want to measure the reflected wave, or actually I should not use reflected because reflected means from the same port by definition, right? So it's the scattered wave or the outgoing wave, because if you look at this figure again, and I will tend to use these terms interchangeably, so just be mindful of that. See, the directions are all over the place because the ports are in a 360 degree here. But the point here is that all the waves which are coming into the network, they are called incoming wave, and those are the ones with the plus, and all the goings ports which are going away from the network, it's called the outgoing wave, and that's the one which is called minus. Okay. So we go back to the definition here. So the scattering matrix Sij is calculated by measuring the outgoing wave at I. So this is important to note that the first index here refers to the outgoing wave port divided by the incoming wave amplitude for port J, with all other incoming wave amplitudes set to 0 except for the jth one. Right? So this is exactly the same kind of thing we said, that all other terminals should have open circuits so that there's no current flowing through them when you're computing the impedance matrix for a particular pair of ports. Here also, the definition is that the Sij tells you that if you only sent in a wave amplitude Vj plus on port J, that you will get an amplitude Vi minus, which is equal to Sij into Vj plus. So that's the definition of the scattering matrix. It's a little strange in the sense that, especially if you're looking at this, the order of the index. See, the order of the index just comes from how the scattering matrix is defined in the standard form. But if you now consider a two-port network, you have a two-port network here, and this is 1 and this is 2, and you want to say what is the transmission coefficient through this, you would have liked to have that is going from 1 to 2, so you might say it's S12, but actually it's S21. Right? Now, in a linear reciprocal system, of course, S12 and S21 are going to be the same, but the destination, which is the outgoing wave, because that's the one you are detecting, is always comes first. Okay, so this is important to keep in mind, because otherwise you'll make mistakes on interpreting what quantity is being represented, and also when you are actually measuring in using a real instrument like a vector network analyzer. Okay, so in fact, the next page has a picture of such a device, and I'm sure some of you have already used this. And a little bit later in the class, we will actually do a demonstration with one of these instruments to see. So this instrument here actually has 4 ports. So 1, 2, 3, and 4. Actually, wait a second. Those are probably, oh yeah, it's 1, 2, 3, and 4. Yeah. So it means that it can measure a scattering matrix of a 4-port network in one go. You can connect all 4, or you can connect only 1, 2, and you choose the quantity to plot, which is S11 or S21, and then you can choose whether it's plotted in its magnitude or its phase, because this is in general a complex number, so it has amplitude and phase information as well. Okay, so yeah, so that's the definition of the scattering matrix. I will not go through this, but this is again very simple. So here again, for a T network, they have computed what the scattering matrix parameters are, and it gives you, of course, this is now a fairly detailed calculation, because essentially you have to compute the reflection coefficient. So the S11 part is easy, because you are saying that I want to measure V minus, which is, sorry, V1 minus, which is the voltage coming out like this, when a voltage is sent in here on the same port, but with nothing being sent on the other port. But, so this is why I said that the characteristic impedance of the system is important, because here it says that S11 can be found as the reflection coefficient seen on port 1 when port 2 is terminated in a matched load. This 50 ohms, right? Not matched to the network, but the network's, sorry, let me say that again. Not matched to anything to do with this guy, but the system of characteristic impedance you're working. So that's why the scattering matrix has depends on this thing you're using here. So not applying a voltage here doesn't mean that you just leave it open. It means that you connect it to a 50 ohm and don't put any voltage on that. That's what it means. Okay. So if you do that, you can compute the different scattering metric parameters. So we can actually now see this maybe as an example in the 10 minutes I have. Let me quickly see. I'll show this in Microwave Office. And this is slightly this idea of having the ports terminated in order to get these numbers is something you need to get used to. It might not be so obvious, and you can really make mistakes in simulation softwares and otherwise if you don't understand this point that the ports cannot be left unterminated when you're extracting these quantities. So, okay, I'm going to stop sharing here. Okay, so I've drawn a schematic here. I'm just going to quickly draw a similar 3-port network. Parameters they used 8.56. So I connect 2 ports. And since these are resistors, there's no frequency dependency. The properties here are going to be the same at all frequencies. So I'm just going to put like, yeah, these 2 points are good enough. And let's look at the graph. S11, look at just the real part here. Anyway, this is a purely resistive circuit, so it don't really have any imaginary parts. So it's giving a very small reflection because I think this one is actually a matched attenuator. But what they said is that in order to measure the reflection coefficient, sorry, in order to measure the S11 parameter, remember that this, I have asked it to plot the S11 parameter, which is, so it's doing that here. But what I wanted to show you is that this is equivalent to, let me freeze this. This is equivalent to the definition they gave. So what was the definition? That I need to put here a matched load of 50 ohms. So I'm going to put this 50, and I'm going to change the measurement not to S11 now, because anyway, S11, I'm changing it because it might feel like cheating. But remember, this is now a different network. But what I'm interested in is looking now at the reflection coefficient, which is gamma, and gamma is where is gamma? Thought there was a okay, maybe I'm mistaken. Is it GM1? Yes. Okay, somehow I thought there was a measurement for the reflection coefficient, but let me just go back to okay. Right. Okay, I mean, it's showing something which is slightly different in some few decimal places, but the first measurement was the scattering matrix element measurement as for the full two-port network, and now I have drawn the equivalent circuit where I have terminated the second port with a matched load 50 ohms and only measuring the reflection coefficient, which is the same as S11 for a single port network. So these two are the same. But the point I wanted to make is that if I remove this, then the reflection coefficient is not the same as S11, right? So now this is giving me a reflection of 0.5, whereas earlier it was basically essentially 0. And the reason is that this is actually a matched attenuator. That if we calculate, if I put a 50 ohms here and I see what the input impedance is, the total will actually be close to 50 ohms. Okay, so I'll do this part again in the next lecture. I'll start with this because this is slightly subtle and give you a few more examples of when you need to consider that the ports have to be terminated in order to interpret the results correctly. Okay, so let me stop there. If there are any quick questions, I can take now. Go. Can't seem to find the window here. Gaurav, are you there?
Yeah.
What's going on?
Hello.
Yeah. I'm not able to find the Zoom window where the okay. Right. Got it. Okay. All right. So we'll stop here and then meet on Monday.